All right. So we're back with the lectures. Last week I was sick the whole week, so I didn't record anything. I had the notes ready. This weekend, some of y'all might know there was a hackathon that was going on, so I was busy with that, so I could not record anything. So a week went by. Plus, I just started my co-op position as well. L- Been busy with a lot of things, but we're back with the videos. This is gonna be a short and sweet lecture, not too long. Um, a little bit conceptual. So we're going to talk about the Zener diode, um, how it works and everything like that, because the Zener diode is a very important part of the next section that we're going to study, which is the rectifiers. So if we get the Zener diode knocked out, then the rectifier part we can actually focus on the way the diode circuits will actually work and how the Zener diode finishes that entire rectifier circuit. So. What is a Zener diode? A Zener diode is basically a regular diode that is operating in the breakdown region. So we've seen before, this is my current, this is my voltage, okay? This is the forward region. An ideal diode would be this blue curve, okay? This blue curve. This is the IV characteristics of a real diode, an ideal diode, sorry, and this is a IV characteristic of a real diode. VZK is the point at which the most negative point prior to which the diode would operate in the breakdown region. So here we have this highlighted section here. This highlighted section, which is to the left of this minus VZK, is called the breakdown region. And this is where the Zener diode actually operates. Now, here is the schematic of a Zener diode. We just have this Z symbol right here to indicate that's a Zener diode. So the only difference from a regular diode and a Zener diode is that, as we've said before, if I have a diode here, it's going to have a voltage across it, V. If that voltage is bigger than zero, the current is going to flow in this direction. If the voltage is less than zero, then there's no current flow at all because no diode is going to allow current in this direction, okay? So the current is going to flow in the direction of the tip of the triangle. That's a definition of a diode. A Zener diode is the opposite of that because if it's in the breakdown region, it's going to allow current to grow to go in the other way. So we'll enter it, sorry. So current will enter from the tip here to the other part of the diode. Okay, it's the opposite of a regular diode. And since current is going to enter from the tip, that means the high voltage has to be on top and the low voltage has to be on the bottom so that there's a potential drop right here. The potential is going this way, right? Electric field this way, so the current's going to flow down. Now, one thing to keep in mind very carefully here is we are operating in the breakdown region. However, here, okay, this current is positive when we're talking about circuits. Okay, this current is positive, and then this voltage is also positive when we're talking about circuits. So that's why I wrote IZ and VZ. Those are positive values in the representation of the standard diode. However, they represent negative values in the IV plot. So if you look over here, we got an IV characteristic here. This VZK right here, it's in the negative side, right? This is the negative. These are all negative numbers. So this IZ and this VZ right here, it represents negative values. So if you're given a question, um, calculate IZ, VZ, and you did, and then the question says, okay, well, what would its value be on the plot? The values that you've got, you would have to put a negative sign in front. So that's something to keep in mind. Oh my God, excuse me. I'm still coughing. I'm still getting out of that cold, but we have to record the videos. So we're gonna magnify this breakdown region here to get a further understanding on this. So this is the breakdown region, as I've said before, the highlighted region. I'm just gonna like increase that breakdown region further. So this is the minus VZK that I was talking about earlier, okay? And then this is the end of the breakdown region sort of because this is gonna it's gonna keep on going but at some point we don't really care. The current is gonna get too negatively large and there's no point. We want to stay where the current is very linear, okay? If you look over here as it goes down like this, I just took this and I just amplified it a little bit, right? I just kind of like expanded, I magnified it. Amplifies are wrong, where I magnified it so we can see what's going on. So this is like a straight line here. So I would say that this is the linear region. Now, if I take this straight line, I extrapolate it, I would reach some point right here. That point would be called right here what I call minus VZO. This would be your minus VZO. This point is your minus VZK, okay? And over here, as I've said, IZ is the current that flows through the Zener diode. So I want to pass a test current value in that Zener diode just to see its linear relationship. Okay, so I will pass a current IZT, a current IZ test through that Zener diode. Okay, and the value of that current IZT is a negative value. Okay, whatever positive value we got here actually represent negative values. So this is the current that I got here, negative IZ test current, okay? Now, if I keep on going here, I extrapolate this minus IZT to a point on a linear curve, and then I go up, this is going to correspond to a minus VZ. Okay, so we have a point here that we're going to call Q, and that point would be minus VZ minus IZT. We want to find what is the voltage when we pass a current IZT through that diode. That voltage would be minus VZ, and we have a point on a plot which is minus VZ and minus IZT. And I've said it here, it's negative for the sake of the graph, okay? So that's all that's going on here. Now, this minus VZK, which is right here in our first plot, is drawn right here, okay? So now there's something to keep in mind as well. So as I've extrapolated my curve right here, we have minus VZO, which is this point. This is still our minus VZK. So if I extrapolate it here, this minus VZK is going to correspond to a minus IZK. Okay, a voltage is going to correspond to current. All right. So now that we got this figured out, there's one thing we need to still do is that we want to find the slope of this curve. Now, let's get some intuition behind that. We've seen in previous lectures that a real diode is kind of like that. So we have a diode in series with a voltage source, in series with a resistor, right? A resistor. Same thing with the Zener diode. There's going to be a resistor involved. And how do I know this? Is because we have an IV curve and we have a linear graph. What is an equation that relates voltage and current being a linear equation? It's Ohm's law. So, however, we need to find the slope of this graph. How do we find the slope? Rise over run. So here we got a rise, which is the same as this, which I will denote as delta I. Here we have the run, which is delta V, which I will denote as the run. And this is a real linear region because, as I've said before, this is a linear graph. So M, which is a slope, is rise over run. What's my rise? Delta I. What's my run? Delta V. So slope is delta I over delta V. Ohm's law tells me that V equals IR. So if I have I over V, which is what I have here, I over V, that would correspond to 1 over resistance. We're talking about a Zener diode, so this resistance right here would be RZ, which we'll call Zener diode resistance. So that's all I did. I just found the slope of this. It's linear. What is one equation that represents a linear curve for I and V? It's Ohm's law. I isolate it in terms of what I want, and there we go. We have a Zener diode, a resistance. Actually, this is wrong. It's not a Zener diode resistance. It's 1 over the Zener diode resistance. Okay. If I want to find RZ, I would have to flip this value. Okay. So RZ would be what 1 over M. That's something to keep in mind. Okay. So Zener diode model in the breakdown region. As I've said, this is a Zener diode. We have a voltage across it, VZ, and an IZ, current flowing through the tip. These values are going to be positive values. On the graph, they represent negative values. So our model for that circuit would basically be a voltage source, VZO, just like the diode we saw in like lecture 1. This voltage is not VDO, it's VZO because we're talking about a Zener diode, and this will be RZ for resistance. And the voltage across it, VZ, will still be the same. Now, if I do a small KVL around this loop right here, we have that minus VZ plus VZO plus IZRZ equals 0. So I can write VZ in terms of the Zener diode elements, and we have this equation. So that's it for this video, and there's not a lot when it comes to Zener diode because we have a lot of background already on semiconductors and regular diodes. So this video is very, very short and sweet. It lets you learn a lot in quite a short time. And my advice would be not to dwell too much on Zener diodes. If you understood this, great. You have a lot of background. Just solve a couple of practice problems, and you should be set for success. However, the next video that is going to start coming, the rectifiers, we're going to start talking about rectifiers, one diode rectifier, two diodes rectifier with center tap transformers. We're going to talk about bridge rectifiers, half-wave, full-wave rectifiers. So those are going to be quite important, and those are going to require much more attention and importance from your end. So with that being said, this is the end of the lecture. Um, I will say something on Fridays, 6 p.m. till 8 p.m. I am on campus at the U Ottawa campus, so I have office hours with the IEEE. I'm the ELG commissioner from 6 to 8 p.m. So if you want to drop by, say hi, you're more than welcome to do so. That's every week, Friday, 6 to 8 p.m. Um, Plus, share these videos, Max. Make sure you watch them the full length if you want to actually benefit from them. Plus, if you want to see more content from an unconventional small YouTuber, please like and subscribe. And until next time.